Recording is started. I just want to make a short recap of what we are doing. Just keep in mind that we have lecture today and then next Thursday, and then we are over. Okay. So as more recap, we are studying the impact of climate change over Earth level. And in particular, what we need to do is, and what we are doing now, is to study how climate is changing, because first of all, we need to understand what are the drivers, the climatic drivers in this case. And therefore, we need to quantify, not just getting a feeling of how climate is changing, but we need to understand in a quantitative way what are the variables, the climatic variables that are going to change. From these changes, these quantitative changes, then we can assess the impact on human health. And of course, in order to make this quantitative estimation, we have to set up models, and therefore we have to understand the science behind it. So we defined what is climate change, and talked about, in particular, global models. Just 1 second, I just wanted to close this one. I don't understand why it keeps, so let me just try to do this. Okay. So we defined, as I said, climate change and talked about, in particular, global warming. And we highlighted the importance of local conditions. So I stressed since the beginning that in order to make a global study, we need at the same time to focus on the local conditions, because the local conditions are those that determine the impact of climate change, and in particular the impact on human health. And in terms of global conditions, I mentioned local conditions, sorry. I mentioned the local changes of climate, because climate change is not something uniform all over the globe, but it's differentiated. There are differences based on the geographical location, based on the land use, basing also in terms of impact on the state of the healthcare system, for instance. And then, as I said, we started talking about science. And we mentioned the greenhouse effect, which is deemed to be responsible of global warming. And we just gave an introduction on how it works. And we mentioned that the greenhouse effect depends on the concentration of greenhouse gases, and the greenhouse gas that is getting more of our concerns is CO2, is carbon dioxide, because we believe that there might be a strong influence of the human component in determining the increase that we observe in the recent past, in recent and not only recent, actually, it's about more than 100 years already, we observe an increase in the concentration of atmospheric CO2, and we believe that there is probably a significant human component. CO2 is not the only one greenhouse gas. There are other gases like methane, for instance, but in the concentration of methane, we believe there is no great human influence. Of course, it is important that we also study the dynamics of the other gases, because if we want to mitigate climate change, and therefore mitigate the concentration of greenhouse gases, we may also study policies for inducing a decrease of other gases like methane. But in order to study the human component, if we are concerned about the anthropogenic driver, methane is not believed to be a gas that is much influenced by the anthropic activities. Also, yeah, please.
Usually, like vegan movements say that methane is one of the leading causes of global warming and such. So, do you think there is no scientific base for that, or is it that the level is increasing, but such a non-influential rate that we can consider it? No.
I mean, the methane is relevant, but the anthropogenic driver on the concentration of methane, as far as I know, it's not very significant. So we don't believe that humans are, when we talk about anthropogenic effect, we talked about CO2 emissions. Methane is relevant, and it's emitted by oceans, by natural processes, but we don't believe, because when we use methane, for instance, for cooling the buildings, then the effect on the greenhouse gases is the release of CO2 that is associated to that, which is not very relevant, but still it's there. So I don't think, as far as I know, that methane in the scientific literature is mentioned as a potential influential driver, but not associated to the anthropogenic component. I'm not sure. So you said that the vegan movement...
yeah, the overconsumption of meat, so it is like cows...
Yeah, I understand. Yeah. I understand, but actually it's in the... A lot of emissions are associated to the farming activities, really a lot. So agriculture is very influential, but as far as I know, it's not. It's more, yeah, more than ever other gas is more than any other gas is CO2, and of course there are emissions by the animals, but it's not really relevant. So if we increase the number of animals, of course there is an increase of methane that is emitted by the animals, but it's not really relevant. And also humans emit methane, but it's not considered to be very relevant. Another very influential greenhouse gas is water vapor. But in this case also we think that the human component is not really relevant on that. And also water vapor has a residence time in the atmosphere that is much lower than CO2. So mainly we are interested in studying the carbon cycle and therefore CO2 concentration. So, as I said, so we talked about the greenhouse effect and we talked about the feedbacks. I'm just making a recap now. Feedbacks between processes, between systems, dynamic systems that are playing a key role in the overall life cycle of the natural environment. So, for instance, the feedbacks from the carbon cycle and the water cycle, the feedbacks between water flows in the oceans, ocean currents, and water flows from the grounds, and feedbacks between the temperature of the atmosphere and evapotranspiration, evaporation plus transpiration. This is something that we mentioned, okay? And we put into evidence that we don't have a full understanding of these dynamics, and therefore we don't have a full understanding of the feedbacks. And we mentioned about positive and negative feedbacks. The fact that we don't have a complete understanding of these processes and links between them, the feedbacks are links, are bidirectional links, means that there is uncertainty in our prediction. And uncertainty means that when we make a prediction, a future prediction, there is an error in this prediction. Keep in mind, uncertainty means lack of deterministic predictability. Uncertainty doesn't mean that there is a lack of statistical predictability. So actually, this is what we do. We try to quantify uncertainty in statistical terms in order to be able to predict it. But uncertainty means that we don't have a precise prediction for the future. So we cannot say that rainfall over Milan at the annual scale, so the rainfall that falls in 1 year, by 30 years will increase 10% or will decrease 10%. We can just draw an envelope, like an estimate with an uncertainty range. And this is extremely important when we want to make the design of adaptation and mitigation options, because of course, if you have a prediction that is certain, you can precisely determine what is needed to mitigate the problem. If the prediction is uncertain, you don't have a precise determination of what is needed, and therefore you have to, in a way, take into account that your design may fail because it's based on a prediction that is uncertain, and therefore you have to set up a plan B. This is not a problem. This is something that the medical doctors and the engineers know how to do. A plan B, a plan C, a plan D, you know, but still, and then I have to say, I believe that you in your discipline are used to uncertainty, as far as I know. Also in engineering, but in other sciences that are strictly related to engineering, and in particular geosciences, not all the branches of geosciences accept this presence of uncertainty. And when you look at the prediction of climate for the future, uncertainty is barely mentioned because, you know, with these sciences that don't have a direct link on the operational solutions, but have a direct link in policy making, it's very different, the role of a climate scientist from the role of a medical doctor or an engineer. Medical doctor and an engineer has to find a solution. Okay, you have a patient, you have to find a therapy. You cannot just talk about philosophy or set up a policy. Okay, there are some medical doctors that are involved in policy making, but the operational activity of the medical doctor is finding a solution, like the engineer. And the operational activity of a climate scientist usually is policy making. And they are concerned that when talking with policymakers, with stakeholders, if they vehiculate the notion of uncertainty, they are concerned that the trust in their judgments may be impacted, may decrease. And therefore, they are reluctant to talk about uncertainty. Just keep it in mind. I think it is instead important that you, as a medical doctors and also engineers, well know that there is uncertainty. So when you listen about prediction of future climate, beware, there is always uncertainty, like meteorological prediction. But with the meteorological prediction, actually, uncertainty is quite reduced. You see that it has been much improved recently. The meteorological prediction have improved a lot in recent times. I mean, if somebody tells you that tomorrow it rains, most probably in Milan, most probably it will rain. If you look on the website of meteorological prediction, for the future climate is a different story. So we have to take it into account. Now, let's continue then with this discussion about feedbacks about science behind climate change. And given that I introduced uncertainty and I dedicated some time talking of it, I think it's time to talk about tipping points. Let me just get the PowerPoint as well. And so I have the figure ready in the PowerPoint. So what are the tipping points? In the Earth system, we have experienced that it may happen that at a certain point, I mean, the Earth system looks stable in a way. And let me see, where are tipping points here? The Earth system looks stable in a way. Why it looks stable? Because it exists. It wouldn't exist nature if it was not in a stable equilibrium, in a resilient equilibrium. What does it mean, resilient? It means that if you get a shock, a perturbation, the system can recover very quickly. We can talk about resilience also for a human body or for a human population. It means that if they get a shock, which can be an health shock or whatever, they can recover quickly. Think, for instance, in my field of a community that is resilient against droughts or floods. It means that if they get into a water scarcity situation, they can manage it and can recover quickly. So if nature was not naturally resilient, it wouldn't exist, because a system that is not resilient is going to die. And this is the mechanism of natural selection, of evolution. So given that nature evolved, life evolved, it evolved because it passed through an evolution, through a natural selection, and therefore it is stable. But on the other hand, we learned that when we talk about the Earth system and natural system, we learned that these systems may have two kinds of equilibriums, two or more. Think of the Sahara Desert, for instance. We know that once upon a time, it was a forest, it was very green, and it was a stable situation because it lasted for a long time. Now it's a desert, which is another stable situation. It means that the Sahara may have two equilibrium situations. You can think the same about a forest. A forest, when it grows up, it's made by brushes. And then in the very long time, eventually, some of the brushes, which are more robust, more resilient, grow up and become trees. And when they become trees, they take all of the light, and the brushes under the forest die. And therefore, the forest becomes what we say in Italian alto fusto, a forest, an alto fusto forest, which means a very tall stands. And this is an equilibrium situation. But if you clear cut the forest, then the forest starts from scratch by growing brushes. And the brushes situation is another equilibrium situation. It's going to last for a long time. So these are examples of systems that may have 2 points of equilibrium. You can think of like an hole, very low depression, and then a peak and another low depression. A drop of water can fall in one or the other depression. So what we learned is that, again, natural systems may have 2 or more states of equilibrium, and sometimes when you reach a critical situation, a critical state, which is between 2 equilibriums, it may suffice a very small perturbation, external perturbation, to change from an equilibrium state to another equilibrium state. Another example is the Lake Aral disaster. Let me just show you a Wikipedia page. This is not a Wikipedia page, it's a PowerPoint. I'm sorry. Let me see if it works. Yes. Let me get in the screen. You still see the presentation. I have to change it. 1 second. I am searching on Google Lake Aral disaster, and then let me remove the presentation because now you should see my Google search. Yes, but it doesn't work. Let me see. Unusual traffic. Interesting. Google.com. Okay, let's see. Lake Aral disaster. Let's see if it works now. I'm not a robot. Okay, motorcycles. Be patient. You know. Let's see if it works. I was not good. I don't know about you, but when I feel these, yeah, stairs was not good, but the motorcycle was quite tough. I think this is okay. Okay, very good. RLC, but Lake Aral disaster, Wikipedia. Okay, so this is a picture. Let me see if there is. This is a picture of the Aral Sea in 2004. It was already decreased in extension. You can see the original extension with the darker area that I'm now depicting with the mouse. And this is in 2004. Okay, you see progress in 2000, 2001. You see that the Lake Aral reduced its extension significantly. So this is, okay, you can see here a nice map, okay, a progress from 1960 to today. The Lake Aral was originally one of the largest lakes in the world. I don't remember the overall extension, then we go back to Wikipedia, and then started decreasing in size. What was the reason? The main reason was not climate change, but it was land use change, because the Soviet Union wanted to take water for irrigating the cotton fields. And they took water from the tributaries, and they, of course, didn't realize that this would have an impact on the overall water balance of the Aral Sea. And then the lake started to decrease its size, and the result today is that it got to another equilibrium situation, because they got also climate change afterwards, because decreased evaporation means decreased rainfall. And nowadays, it's not possible to put it back, because in order to put it back, it's not just enough that they stop taking irrigation water. You would have to put water in there, which is, of course, not possible. So this is another case where even a small perturbation, because they didn't take all the water from the river, they took a significant amount of water, but not so much. A small perturbation brought the system from one equilibrium state to another equilibrium state. It's interesting if you look at these images in Wikipedia, and you see it now, the situation is like this. And also the area is salted, because so it's not possible to cultivate it because of the concentration of the salt in the lake that went into the soil. And so there are indeed a lot of interesting pictures over the web. And the original extension was, I tell you, the RLC since, let me see, the original catchment area. No, this is catchment, it's not surface area. It was the original surface area in 2004. It was not the original, it was already reduced, was 17,000 square kilometers. To give you an idea, the Lombardia region, I think it is extended like 40,000 square kilometers. So it was really huge. And if you look at the original extension, probably is something like, okay, it's here. It was in 1990, 68,000 square kilometers in 1960. Okay, 68, almost 70,000, and now less than 15,000. Okay, this is another example, as I said.
Now, are there any buildings in the area in which there was the soil is just?
No, because it became a desert, because you cannot cultivate it. There is a shortage of water.
I mean, like buildings.
Buildings.
Yes, in that area, since it's so extended.
No, it was not urbanized. It's not yet urbanized. I know that there are recovery plans, but I don't know the details. And recovery plans try to at least preserve the part of the lakes that remained. But it was not urbanized because it's an area that offers very few reduced resources. So I was talking about tipping points. So let me just show you. So these are a concern, you understand, because what is the concern? The concern is that with this global warming, we may cross a threshold after which we have a sudden change in some parts of the Earth's environment. So for instance, here you see a map that is very popular, is over Wikipedia, which highlights what we think are the most relevant tipping points. Probably the most popular, the most known tipping point is the tipping point related to the polar caps. The Earth in its history didn't always have polar caps. Actually, if you look at the history of Earth, the presence of polar caps is limited to glaciations. We are still into a glaciation, into the tail of a glaciation. So we are used to have polar caps, but in the history of Earth, these polar caps didn't exist, didn't ever exist, okay? Which means that in some period they existed, now they exist. But there were periods with higher temperature due to natural changes, natural variations, where the polar caps didn't exist. And the question is the melting of the polar cap that already occurred in the past something that occurs suddenly or something that is very slow? Because remember, if you have slow changes, then you have time to adapt. People have time to adapt, and then you don't have really a big societal impact. You don't have wars, tensions, but if something occurs unexpectedly, think the pandemics, for instance, then you have a big impact because the society doesn't have time to adapt. During the pandemics, at the beginning, we didn't have time to produce masks. And therefore, these tipping points may be concerning because let's go back to the polar caps. The question is, do they melt slowly, or can they just go down very quickly? And you may think that reasoning brings us, intuition brings us to think that it must be slower increase of temperature, because what we observe is not a sudden increase of temperature. It's something that is rapid, but not so shocking. It's not 10 degrees in one time. So we may think that it is slow, but actually, it may also be very quick. Why? Because we discovered recently and this is a recent discovery, that within the polar caps, in the deep ice, there are huge lakes. And the reason is that with the pressure of the ice that is above these lakes, the water cannot get iced, because you know that in order to freeze, the water have to be allowed an expansion of volume. If you don't allow water to expand, because there is really a strong, like a strong bottle, then the water doesn't get iced. And this is how we obtain liquid water that is under 0 degrees, a lot under 0 degrees. If you put a lot of pressure, then we can keep water liquid. And these big lakes, if the thickness of the ice decreases, then they may break suddenly. And we indeed already observed some of these phenomena. But we don't have still a clear mapping of these lakes that were only recently discovered. They exist both in Greenland and in the Antarctica, but we don't have still a complete mapping. There are ongoing research projects using different techniques trying to map these lakes. And within other research projects, people put a lot of cameras because they want, we hope, to be able to get documentation on one of these events, the break of a huge lake. And you understand that these events may cause a rapid increase of sea level. And so this is our concern. Like, may it happen that in a time span of few years, like 10 years, we get completely de-iced the polar caps, which would cause a consistent global warming. We don't have a reply for this. We don't have an answer. And our models then cannot predict these kind of events. So you understand uncertainty. Uncertainty means that there are some dynamics that we still don't know, and this is one example. Other examples you see here: instability of the Indian monsoon, Sahara greening, as I already said, and West African monsoon shift, or boreal forest dieback. It may happen, a dieback of Amazonas rainforest, or change in global circulation. The ENSO that you see on the left, it's the red spot on the left. ENSO means El Nino. El Nino, you heard about El Nino, because sometimes people say we are getting flooded or we get a drought and the cause is El Nino or La Nina. What is El Nino? It is simply a temperature difference in the Ocean Pacific between the coast of South America and the coast of Australia. They measure these two temperatures in the deep ocean, and there is a difference. And this difference triggers movement of water, because warm water expands and tend to go towards the areas with lower temperatures. So you have movement of warm and cold water. Typically, warm water is up and cold water is down. Okay, and warm water means evaporation. So you bring humid air in one side or the other side, which means flooding, or may mean droughts, because you don't get, if you get dry water, dry cold water over a region, which may persist for a long time, because El Nino may last for even for a couple of years, because you know this change of temperature in the ocean, Pacific Ocean, is huge, it's very deep. It takes some time to revert, and therefore these global circulations mean that you may get an influence over climate, and they may determine sudden changes in climate and determine from one equilibrium to another equilibrium. So these tipping points are indeed something that we cannot predict, and therefore, what could be our B plan? Our B plan could be, let's make an estimate about the polar caps of the sea level rise that we would get if the polar cap suddenly melted. And therefore, besides making a prediction of the sea level in 2100, which we make with models, and these predictions say that the sea level rise in 2100, if nothing really bad happens, should be contained into max 50 centimeters from now. But besides making this prediction, let's also make another prediction, very skeptical one. Let's eliminate the polar caps and let's see what happens. And indeed, the change would be much higher. You can think about you can think of the sea level rise during the glaciation. It was minus 120 meters with respect to now during glaciations because of the volume of water that was kept by the glaciers and the polar caps. So I'm not an expert about the sea level rise that we would get without polar caps, but I guess it may be like 10 meters or something like that. And it is an information that we may easily find. And so I'm not really involved in these activities because I am an engineer, not a climatologist. But the B plan in this case would be to try to make another estimate, another prediction, like a worst case. So these worst cases in the presence of uncertainty are very important. This doesn't mean that you have to get protected against the worst case, but at least you have to know. And in engineering, it is very typical. So when you design a dam, for instance, and then you have to make sure that the dam doesn't fail if we get a big flood, then we make the estimate of the big flood, but at the end of the story, we also make some estimates of a worst case. Let's suppose that we get a really big one, okay? I'm sorry if I close the door. So let's suppose that we get a really big one.
So what, I also have a question about the...
Please.
You said that water stay liquid when there is a lot of pressure.
Yeah.
And so the point of the lakes in the Alps is that there is this very big level of ice that produce pressure on the water that's under.
Yes, yes.
And so increasing of temperature is making the ice melting.
Yes.
But what about the breakage? Because how the sea level can increase with the breakage of the, it's not clear for me the mechanism of movement of water towards the sea.
Because if you get a decrease of the thickness of the ice, then the ice goes down. Of course, it starts from the surface, goes down, and can get to a point where the thickness over the lake is making pressure because the lake is under pressure. So basically, water is incompressible, or let me say, water is not highly compressible, but it is compressible. And we experienced this in several applications. If you put a lot of pressure over a volume of water, you get some very limited compression, but it means that water gets a very high pressure. So basically, if you decrease the thickness of the ice, then the water can break it because it's under pressure. And therefore, and don't think of the fact that if you decrease the thickness, you may think decreasing thickness means decreasing pressure and the water gets iced. No, actually, there is inertia in the system. So what we observe, indeed, not directly, but we got the remains of some lake outbursts, glacial lake outbursts. What does that mean? That you get suddenly a lot of water flowing over the surface of the ice that comes from the interior of the ice. Keep in mind that it's not flat. There are mountains, it is a sloped surface. So if you get a sloped surface to break, then you have a sudden outburst of water, which forms like a river over the ice and gets into the ocean. And the same happens when you get warm, for instance, during this summer, the glaciers over the Alps were in a very good condition because we got a lot of snow during the winter. But then the summer was warm, and therefore we observed the formation. There are several videos on the web of rivers over the ice, because there was a lot of snow that started melting, and the water was flowing over the ice. There are videos of people that were skiing like nautical skiing. I'm not sure if it is correct to say nautical, but ski nautical, over a glacier, because there was a lot of melting, and we know this phenomenon. So it is indeed possible, and we don't have time, but if you look for glacial lake outburst, I think you find some information. It is not really relevant to you, because I mean, it's let me just check. I think I had okay, let's do it later. Okay,
but at the same time, does mean that for example, like an higher pressure does also mean higher temperature, like in the system as well?
Yeah, it is about 0 degrees, yes. And no, it may be lower than that, because if you have a higher pressure, the water is under, how to say, it is liquid under the temperature of 0. And there is a term in Italian which I cannot translate, but it is like liquid water in frozen conditions. And you can also make an experiment. Usually, when you put a bottle of water into the freezer, and the bottle of water, bottle of water typically breaks. Because there is expansion. But if you could measure the temperature inside the bottle, you would see that before breaking, before icing, it gets to a temperature that may be -10, because if you put a lot of pressure, then it cannot expand, and the result is that it doesn't get iced.
And outside, in the environment in which these lakes form, how much is the temperature?
The temperature in Greenland during the winter may be -70. Yeah.
So it's like in the liquid part of water. Of course, it's higher than no. It's in this case it's lower than 0, but still it's higher than the outside temperature.
Yes, it is higher. Yes, usually when you go fully into the ice, the temperature should be 0. But if outside is very cold, then the temperature also of the ice body becomes lower than that. But if it is very deep, it is around 0. It is around 0. Yeah. Okay. So these tipping points again mean that there is uncertainty, and therefore once again we have to make a B plan. Okay, let me just move forward. So it is okay. So these are what are called social tipping point. So tipping points in the societal system. These are easier to understand probably, because it is easily understandable that also a social setting, a societal system, may have two equilibrium situations. Think of a form of governance. It can be a republican, it can be a dictatorship, and sometimes it's in equilibrium. The dictatorship may be in equilibrium because we see many countries where there is a relatively stable dictatorship, and in some of the cases, the citizens may be also not very unhappy with that, because if the dictator is a wise person and makes sure that their power is durable, it has an interest. They have an interest to keep the situation stable. So there is also justification for this, and therefore, but it may appease a small perturbation in order to change from an equilibrium state to another equilibrium state. And these tipping points in the societal system are extremely important when we come to the evaluation of the impact of climate change. Because if the societal system is resilient, robust, like the natural system, then the impact may be in a way lower, manageable. If the societal system is not robust, it may be is in a critical state. It may be that even a small change of climate causes a big impact, a sudden change from an equilibrium state to another equilibrium state. And so this in climate change is extremely important. So when it comes to the evaluation of the consequences of climate change, think of the healthcare system. If it is robust, you have a perturbation in an external perturbation, which may have an implication on the health of people. But if the healthcare system is robust, the implication can be managed. If the healthcare system is not robust, like for instance the Italian one, now there is the belief that it's becoming less robust. So of course it becomes more concerning. And for instance, in my discipline, we are concerned that by the river maintenance. The river maintenance is lower nowadays than in the past. In the past, it was really a big issue. People were involved in the community also on a volunteer basis. They dedicated time to river maintenance. Maintenance means that you check the levees, check the condition of the riverbed, and maybe there are too many trees, too many dead trees, and people were working for cleaning everything or filling the holes digged by the animals because there are some excavating animals that they build their home into the levees because they want water, and the levee is an ideal situation. They don't want to be bothered, and the levee is an ideal situation. So, I mean, we are much concerned by the decrease of these maintenances, and we think it is something that may make the impact of climate change more relevant, because even a small, variability, I'm not saying a perturbation, a variability in climate, a variability in river flow may cause a disaster. It is an interesting combination of these different systems that makes the impact mitigated or more relevant. And this also suggests for you how to adapt to it, how to, in a way, decrease the risk, making the healthcare system more robust once that you know the risks. This is important. So this is the science behind it, and we will see just a little bit later how we use this knowledge to make a prediction. Because actually, if you want to evaluate the health impact of climate change, as I said, you need to make a quantitative prediction. So we need the scientific basis. We will see how, building on this scientific basis, we can make a prediction. But there is one other thing that is extremely important to form up our knowledge: big data, climate data. Climate data is an essential element, an essential information for us, because the reasoning is that we look at what happened in the past, like we do for the polar caps. We put cameras because we want to see what happens in order to instruct our models, to check our models. You build a model to make a prediction. The usual way to check it is to try to predict what happened in the past. It's called also hindcasting. Okay, not forecasting, because forecasting means that you look in the future. Hindcasting means that you predict the past in order to test the models. Okay, and so the data are an essential information. The problem is that we don't have a lot of climate data. I think I already mentioned this to you. People didn't start much far away in the past to observe climate. Observing climate is relatively easy. Measuring temperature, I think that also ancient civilizations could do that. For sure, they could measure rainfall, but they didn't. In some of the cases, like the ancient Egyptians, they observed the river level, because the river level was something, it is very easy to observe it. And it is something that for them was very important. So they observed the Nile River level for about 600 years during their civilization. They used, in order to make this measurement, they used the Nilometer, which you can find here. There is a nice picture. Some of my colleagues also visited it, and it is this one. It is a kind of a staff. You see this column? Yeah, because I am under presentation. Now Now you can see it. It is like a stuff, you see, that goes deep into a kind of well. Well means a vertical hole in the soil. And the well was connected with the Nile River. So the water of the Nile River would get into the well. And for the principle of the communicating pipes, the water was able to go up along this well, along this vertical column, and left a marker over this vertical column. So every year they went down along the stairs and made marked in the stone the level reached by the Nile River, and then they cleaned the column. And this is the way they measured and it's measured the Nile River level. Of course, not every day, but we have measurement for we have 636 measurements annual top. And this is a very interesting situation, very interesting information in order to get an example of climate variability. Okay, let me just go back to, here we are. Okay, this is a very interesting example, as I said, of climate variability. But besides these few spots, actually we don't have a lot of information. When we refer to climate, we define the so-called instrumental period, the period during which we started collecting measurements of temperature at the global level. Global means that we had several stations. And conventionally, the start of the instrumental period is fixed at 1850. I think I mentioned to you that in Italy we started to observe daily rainfall around, on a regular basis, 1700 in some cities. In Padua was the first one, it was 1725. Also in Bologna it was 1730. And so we have a kind of long information, but you understand that it's 200 years, maybe 300 years, so it's nothing. It's nothing with respect to climate variability. And then what can we do to get more information? Because it would be really interesting to understand what happened in the past. This is an example of, this is the annual time series of rainfall in Bologna. When you have this long, you see it dates back to 1813, and it's still continuing today. So it's not complete here. Here it's stopped at 2011, but I recently had a paper on it, and we extended the analysis up to 2023. What you can see here is that there are changes. There are changes, and it is important that we try to understand these changes. What was the cause of these changes? You see, for instance, that the droughts are marked in gray. In the past, apparently, there were more droughts. When we analyze these long series, there is the issue of uncertainty, which is not constant in time. So even when we look at global temperature, we have a measurement from 1850, but recently we had an increase of the number of thermometers. So the question is, how was that influencing the result? For instance, for this series, there were several studies demonstrating that there are some breakpoints, probably when they changed the instrument, because the instrument was not always the same. They changed it. So when you change an instrument, of course, there might have been some issues, but still, this is quite a very relevant information. For sure, this kind of rainfall series are a unique information worldwide at the global level. It's an incredible amount of information that we have in Italy, in Europe in general, but especially in Italy, because in Italy, of course, we had the Romans, we had civilization that lasted for very long times, and were used to observe, at least qualitatively, the Earth system. But it's still short, so what do? We refer to paleoclimate data, like 3 rings. And the 3 rings are an essential piece of information. At the annual level, they don't give seasonal information, or let's say, in some of the cases maybe, but in general, it's an annual information, which can last for a long time. We have 3 rings that are 1,000 years old. And there are also other proxy data. Proxy means that it's not direct observation of rainfall or of temperature. It's we observe variables that are connected. They are proxy, not direct observation, but they are connected. And then we have to estimate how they are connected. So there is an additional uncertainty, because when you measure the tree ring, the width of the tree ring, it's quite precise. But then there is the association between the width and temperature, which is subjected to uncertainty. So this is another question: how can we make use of this data? But actually today there is an increasing interest in this kind of data. And yeah.
What kind of information gives the tree rings? Just the temperature?
Let's say the information that it gives is on the growth of the tree. And the growth of the tree is related to the state of the environment. So the tree needs a good temperature, depending on the tree. And we know the tree, what kind of tree is, and water. So basically you get information about temperature and rainfall. This is what what we observe is that there is a correlation in the instrumental period also between tree rings and river flow. Why? Because if there is more rainfall, then you get a higher river flow. So we are starting, the international community started about, I would say, 30 years ago to reconstruct paleo river flows basing on this proxy data. It works quite well for tree rings in the Americas. In Europe, for some reason, it was not so popular. I tried the reconstruction of the Po River, which I think came out quite well. And but there is a lower correlation, and probably it is due to different climatic conditions. But still, it works, and it is relatively new. And but it is interesting. There are, if you go to the web pages, let me just go out from here. From my web pages, there are the links to these are data from the National Atmospheric Administration of the United States, and you see it, yes, paleoclimatology. And there are some interactive tools for downloading the data. Here there is no graphical representation, but if you go here, you see that there is a GIS. Just 1 second. And in the meanwhile, I open another window where, okay, let's see. Yeah, no problem. Yeah, no problem. No problem at all. So here is a map of the proxy data, and you see the kind of data we may have. Bore a hole, it means carats of soil. And then from the carats of soil, you see the sediments, you see this the sequence of the sediments, and you can reconstruct the climatic features. Corals, you look at the corals and the rate of growth. And historical data means where you have the historical information. Ice core, this is another very good piece of information, because if they take these cores like carats of ice, and they go back for 1,000 kilometers. And in the ice, there is information on the atmospheric composition, because you get like CO2, you get the concentration of CO2, for instance, and many other information.
Also, maybe bacteria and
yeah, also this kind of, yes, and also this kind of information. I'm not an expert, but I can tell you that I am a user, and it is indeed interesting. And here you may find also, you may search for a location, and this is something that is not relevant directly to you, but I think it's important that you know the kind of information that is used to make predictions. And this is another interesting story. It's the Old World Drought Atlas, which gives a reconstruction of droughts over, in this case, Europe. And the counter here starts from the year 1000, or from the year 0, and it's moving forward. What is displayed here is an index that is related to June, July, August rainfall. let's not get into the details. It's called the Palmer Drought Severity Index. And basically, as I said, it's related to summer rainfall. And now it's going to high speed, and also the resolution, the scale of the colors doesn't allow you to get this. But if you would make a refined look around 1200, around here, there has been over Europe a long drought which lasted like 100 years, and around 1200. So this is another interesting, I am using this a lot in order to try to reconstruct the flows of the Po River in the past. And what is the conclusion? The conclusion why we do these studies, and I can give you as an example what we concluded for the Po River. We observed that in the past, indeed, I think it was a little bit later than this, we had a long drought, a very severe drought. I think it was around this period here. In Central Europe, over the Alps, there was a severe drought period. And then we compare these reconstructions that are made with 3 rings. We compare them with the reconstructions that are made with climate models, so a different piece of information. And the climate models, the nice story is that besides reproducing the past, they can make a future prediction. So we observed that in the period 1000-2000, between climate models and paleoclimatic reconstructions, there is quite a good agreement. And then if we look at climate models into the future to 2100, so in a way, this validates in terms of droughts, the predicting power, predicting capability of climate models. And if we look to the prediction of climate models up to 2100, basically we see that it's not unlikely that some very dry period may occur, which are comparable to those that occurred around 1400. Which is, I mean, something reasonable. If something happened in the past, it may happen into the future. On the other hand, if we relied only on the prediction by climate models, we couldn't trust it because, you know, the climate model is uncertain, we know that. But having validated, tested the model against another independent information and having adjusted the model based on this other independent information, then we think that the added value of this prediction, the uncertainty of this prediction is reduced. And indeed, this means that we have to be prepared to that it may occur something like a drought that lasts for tens of years. And, you know, in the past, it was a disaster, but today it would be an even more relevant disaster, more concerning disaster, because the exposure of the population is very high. We will learn what is exposure, but basically it's the value of the societal assets, not economic value, the value in a generic way. We have a much higher exposure, meaning that the damage that we would get from a similar disaster, a long-term drought, would be much higher. Think, for instance, at the number of people. The number of people is maybe 5 times with respect to 500 years ago. Okay. So we use this data, and these data are, in a way, we can have several kind of proxies. There is also sedimentation inside lakes and etc. And we also use data of climatic impact, which means that in order to understand damage that we may get from a flood, now people are building very interesting databases of climate impact. So if you look at this figure here, it dates back to 1980. it's the losses from weather disaster worldwide. And it's public domain data. I made this graph by looking over the web and data that are collected typically by insurance companies. And you see that there is an increase of the losses, okay, as you may expect. And this is for sure true. So we may discuss about if the frequency of these disasters is increased. This is really something not well defined. Keep this in mind. Despite climate change, if you look at the frequency, if you just look at the river flows, it's not so clear that there has been an increase of the river flows. But if we look at the damage, it is increased. On the other hand, this second picture is damage divided by the gross domestic product. And you see that it's more stable. So what does this mean? It means that the damage is also related to the exposure, the societal development, not only to the hazard. We will define hazard exposure just in a matter of an hour probably. So these information are extremely important. And keep in mind, we make prediction of future weather, and how we make them. Let me just now go to this lecture that was not here until today. And we got this information, this prediction with climate models. And I put this lecture available, but I just want to mention it a little bit. And I don't want to dedicate much time, but I think it is quite important that you know how these predictions are derived. Climate models then are mathematical tools which allow us to make prediction of future climate. And before starting and discussing them, I want to make a break, but after the break we'll discuss them, but I want to introduce a concept. I already said that these models are subjected to uncertainty, fine. Uncertainty depends on the type of variable. Temperature is easier for the very simple reason that is more stable. It's not subjected to sudden changes in time and space. It is regular. So temperature is quite fine. I mean, the predictions that we made of temperature are quite good. When you go to the variables that are probably more important for the impact on the human health, temperature is also important. But if you look at rainfall, it is, again, extremely important because rainfall causes floods. If you look at wind, wind causes windstorms. If you look at hurricanes, of course, they cause flooding. These are variables that are extremely important. On the other hand, these variables are affected by a great variability, both in space and time. They are much more difficult to predict. So keep in mind, when you hear about a prediction, future prediction of temperature, then you can trust it more than the predictions of rainfall and wind and chaotic processes, turbulent processes, okay? So the dynamics of rainfall is dominated by turbulence, it's atmospheric turbulence. The dynamic of flooding, yes, there is turbulence because in the rainfall runoff transformation, rainfall river flow transformation, there are chaotic processes. So the result is that these variables are more homogeneous, are affected by time variability, and are very difficult to predict. So when we listen about a prediction of rainfall in the future, just raise this question. On what kind of model is based? Is data analysis or is a climate model? What is this? Because one thing is data analysis, which is based on past observations, and we look at past observation of rainfall, and we see if it is increased in the past 30 years. One other thing is a model predicting rainfall, which is basing the prediction on an analysis of the dynamics of the system. there is much more uncertainty. This doesn't mean that we have to discard the model prediction. The model prediction is extremely important because it reflects our knowledge. But on the other hand, we have to understand the difference between a prediction that is made by a climate model and a prediction that is based on data analysis. Okay, and if you look also at the predictions by climate models of past rainfall, it is affected by a lot of uncertainty, and there is no way of eliminating it. Because if you tune the model on rainfall over Milan, then the model becomes distuned, not tuned for the rainfall in Bologna. And it is really complicated to adjust a model to produce a good representation of rainfall everywhere and anytime. So you get some models that make a good prediction of summer rainfall, but then during the winter they are completely gone. Okay, and you get some models getting good prediction of floods, but for droughts they are gone. And this is typical of climate models. We know that for the extreme, the upper extreme of rainfall, it's quite okay. For droughts, for the processes that last for a long time, a drought lasts for at least several weeks. Rainfall, a flood lasts for maybe 1 day. So short time means that it's easier. For a process that is long lasting, we know that for droughts, the climate models are not good. So for making future prediction of droughts, we have to rather look at what happened into the past. And this is why the Po River, we looked at 1,000 years ago in order to understand what is the performance of the model. And for the Po River, it looks like the performance of the model is not so bad, but the Po River is one river. You can't say that then is good for the other river. Absolutely, because there is space variability. So this is what you have to keep in mind. And then I want to discuss with you just briefly how this model work. But I think that now we can make a 15 minutes break. And I will make today, given that I started quite later because the room was crowded, just one break if you agree. Okay. Good. Questions? Okay. So, climate models. How do they work? I think it is interesting to look at this picture, which it is used also later on, because essentially it conveys the information that I would like to give to you. So you see a grid over the globe, a grid that covers the globe in, let's say, in the horizontal direction. Of course, if you look at the globe, it's hard to say horizontal, but it covers basically the surface of the Earth in what is an horizontal direction at local scale. Okay? And then there is also the grid in the vertical direction. So the grid covers the whole Earth's surface, and then it goes down into the interior, so that the whole volume of Earth is divided into like cubes, neighboring cubes. Why is that? Because the model equations cannot be applied to the full Earth. We have to subdivide the Earth in elementary volumes. Why is that? Because if you apply the equation at the whole scale, you would get a description of an average of the variable that you are interested in, like average temperature, over the whole globe. But if you want to describe the spatial variability, which means along the horizontal directions and along the vertical, space has 3 coordinates. If you want to describe the variability along each coordinate, then you have to apply the models on the elementary volumes in order to get a description for each volume. And of course, the smaller the volumes, and then the more local the description becomes. Again, to describe heterogeneity. And this means that actually the model runs are many millions. It depends on the size of the elementary volumes. If the size is much small, then you get millions of elementary volumes or billions. Because if you think that the modern models work at the resolution of 1 kilometer, which means that the cube has a size of 1 kilometer, it means that, you know, to cover the whole Earth surface, you have to you obtain millions or billions of elementary volumes. And therefore, the model runs becomes several model runs, which means computational effort. But there is one more thing to say. These volumes cannot be disconnected, because once that you get a description of the variable in each of them, you have to connect this description to the neighboring ones, because you can't make a separate description, of course. And also because there are transfer of matters between one elementary volume and the neighboring ones. What I mean with matter, for instance, think of water. There is transfer of water along the rivers, in the underground, and therefore when you solve the problem in an elementary volume, you get an estimate of the water that is transferred to the neighboring ones. And then you have to use this simulation when you apply the same model to the neighboring volumes. So you understand the complication. It's quite complex. You understand why these models actually take some time to run. At the beginning, we started with a very coarse resolution, like a resolution of 25 by 25 kilometers, which means a great simplification. Or at the very start, actually, because the first climate models were proposed in the 1800s. And at the very start, they applied just a unique equation to the whole globe. But then they obtained a description of the global temperature. And then when the computers came, people started to work at the local scale, at the beginning with large volumes, and then we are aiming to 1 kilometer. Actually, we can reach with the modern computational resources, we can reach quite easily at the global scale a resolution of 25 kilometers. and we can go down to 5 kilometers only with very supercomputers like the Leonardo in Bologna or other supercomputers that are only available at few research centers around the world. This is why when you listen about climate simulations, you may hear about, they mention some research centers like the Hadley Research Center or the National Atmospheric Administration of the United States, because only a few resources are available, computational resources worldwide. They are increasing a lot recently. So we may expect some improvements in terms of model availability, data availability, and also ChatGPT is a typical sign of this improvement, because this software, in order to run, they need supercomputers. And how these models are called? They are called global circulation models. Circulation is meant to be circulation of matters, and so GCMs. The acronym is GCM. The plural is GCMs, global circulation models. Typically, these models use differential equations. Differential equations means, very simply, that the equation don't describe the variables, but describe the differences of the variable between one volume and the neighboring ones. Because by describing the differences in the variable, they can describe the fluxes between a volume and the neighboring ones. And therefore, they are called these equations that probably you know better than me what a differential equation means, but I want to explain in very simple words. Because usually, also in engineering, when students hear about integral and derivatives, differential equations, they get scared. Actually, it is very simple. Instead of describing temperature as a variable, you describe the differences in temperature. And this is a differential equation. But actually, in order to apply these equations that are very simple, actually, to the whole globe, you get a lot of complication. What are these equations? Typically, they are conservation equations. You can describe almost everything in the Earth system, not everything, but almost everything, by imposing mass conservation, using mass conservation and energy conservation. And actually, I said almost everything because it's not true. That is, we can describe everything in this way, because when we get into the chemistry and the living processes, we need also additional equations. So basically, conservation of energy and the conservation of mass are the basics for physics. So you can describe the physical processes. But when you get into the chemical processes or the ecosystem processes, you need other equations, additional equations. But actually, with the conservation equations, also called the transport equations, you can describe almost everything. They are based on the so-called Reynolds theorem, which is a conservation equation. And it is interesting to notice that all the physical processes we are interested in can be described with two simple equations. Simple. And simple why? Because it's a conservation. So conservation of mass is very simple. When we model rivers, we just say that we take an estimate of the water entering into the river, an estimate of the model of the water outflowing, and then we can describe the storage. This is a conservation equation. It's very simple. But of course, when you apply it at the global level, it becomes complicated. I think this is what you need to know, and because this allows you to understand the complexity and therefore uncertainty. You can understand that it's uncertain, at least because you have to simplify these processes. Because if you wanted to describe everything, and this is what digital twins aim to do, digital twins are defined as digital reproductions of the whole Earth system or part of it. Digital twins aim to reproduce everything so that you can get a digital mirror of the reality. And of course, this is much useful because, I mean, once we have a digital twin of the climate system, we can change the CO2 concentration and then see what happens in the future. It would be really, it is indeed interesting. And let me just skip something. You see here, simple models, energy balance, and radiative transfer. This is an additional equation, actually. And it is complicated because the Earth system, it is composed by, it's a unique entity, but actually, if we wanted to study it, usually we divide the Earth system in some subsystems, atmosphere, cryosphere, which is the domain of the iced regions, and hydrosphere, which is the domain of the water cycle, and biosphere, the domain of biological processes, and technosphere, this is a recent addition, is the domain of the technological development, because we realize that now if we want a modern nature, we have also to include the human component. And in everything, also in hydrology, when we study rivers, we realized, of course, that if we don't take into account dams, the position of levees, etc., we need the human component. And this is what actually most of the climate models miss. They don't have the opportunity of taking into account the human component in terms of land use, human management, etc. And so describing these processes, you understand it's complicated, and we need simplification. We need to simplify. And simplifying means, of course, uncertainty. On the other hand, simplification may lead to more robustness. Just to give you an idea of the complexity of the whole system, this is additional information that I give to you. I think the relevant information is what I just said. Additional information. Look at the distribution of water over the Earth. If we look at the total global water, this is something that you may keep in mind. Fresh water is only 3%, between 2 and 3%. 97% of the water is salt water. Okay, and if we look at, in the middle column, if we expand fresh water, about 70% of the 3% is not usable because it's glacier and ice caps. And you see, it's a lot of water. At the global level, it's not so much because it's about 2%, but it's a lot of water. And then groundwater is a significant percentage of fresh water, and then we have the surface water, which is only 1% of the 3%. On the other hand, keep in mind that this picture is a static picture, which gives only a partial view of reality, because you may get the feeling from here that the surface water is irrelevant with respect to groundwater. Actually, most of the water that we use, not really most, but I would say at least 1/3, comes from surface water. Why? Because surface water is moving. Groundwater is still moving, but very slowly. Surface water is moving quickly. What does this mean? It means that even if you take a picture with a fixed time, surface water looks like a tiny portion of the total. The fact that it's moving means that when you use it, it's immediately replaced, immediately replenished. Groundwater is a different story. When you use it, it takes years to get back, which means that actually, if you consider fluxes and not only the volume, surface water is important. And this is why it is exploded in the third column. In the third column, we see that 2/3 of the surface water cannot be used. Rivers are just a tiny portion, but the water is moving. And also keep into account the fact that water is moving, it's also good for the quality. Because if it is moving, it means that it gets cleaned quickly after a pollution, after a perturbation. Something that is steady, like a lake, absolutely, we have to avoid to get it polluted. This is why the sewer systems do not release into closed water body like lakes. They release only the wastes, only rivers after treatment, of course, not everywhere, but hopefully after treatment. But even after treatment, we don't release it into a lake. We release the wastes, either we reuse them or we release the wastes into the surface water system. So you understand that describing such system with mathematical equation is extremely complicated. describing the water cycle. And this is why the water cycle is usually described at the local level. So it means that our focus is restricted. It's not global. There are attempts also to make global models for everything, but it is really, when you come to the operational practice, it's not the best solution. The best solution at the local level is, in practical terms, operational terms, is to use a climate model to describe the climate, because the climate is indeed something that needs to be described at the global level. You understand why? Because everything is connected in the atmosphere. But when you look for the local effect, like flooding, and as a medical doctor, you are interested in flooding because it's a cause of human injury, then flooding, it's better studied at the local level because it's not connected. I mean, if you get the Po River, it's not connected to the Danube, or yeah, they are connected through the ocean, but flooding is not connected. So this is why typically people who study these processes, they couple global models for climate with local models for hydrology or whatever we study, okay? Maybe also landslides, they are studied at the local level. I would say that this is what I wanted to say to you. And just to give you an example, this is an example, you don't have to learn this, a very simple example of climate model. I think it is an interesting example. It considers the whole system as a whole, as a homogeneous entity, and then it imposes the equilibrium of a radiative equilibrium, an equilibrium of the energy coming from the sun and the energy that is radiated by the Earth. It's a very simple equation. I mean, you take into account the solar constant, the incoming solar radiation per unit area, which we know what is on average. And then you take into account the reflected radiation, and then you come to a very simple equation. Once again, I'm not interested, I mean, this is the energy balance, radiative balance, radiative equilibrium. Equilibrium means balance. You have temperature here, which is unknown. Let's suppose it is unknown. We know the solar constant. We know the radius of the Earth. And let's suppose that we have also knowledge of the albedo, which serves in order to understand how much is reflected. And then we can derive capital T here. And then it's here, capital T. It's a very simple equation that gives to you the average temperature of Earth, which is about 15 degrees, which is precisely the average temperature of Earth that we observe. But you see, this is a very simple example of a climate model that it works. But on the other hand, it's only a very simple balance. If you wanted to estimate, for instance, the increase of temperature due to the increasing concentration of CO2, then you have to change the albedo. And then, you know, it becomes complicated to understand how the albedo changes after the greenhouse effect. And then you have to look into more details. You have to describe more processes. I think this is enough. And one thing. When no, this is important actually. When we make the simulation of climate, of future climate, of course we want to take into account the effect of increasing CO2, increasing concentration of greenhouse gases, and then by assuming that the dominant anthropogenic driver is CO2 concentration and the CO2 emissions by humans, then we have to make a prediction of future CO2 emissions. And these are called the emission scenarios for the future, which are defined, they are several, starting from, let's look at the last one, RCP 0.5. RCP stands for, just one second, I don't remember never the meaning of these acronyms, and okay, anyway, it's an emission scenario. I'll tell you the meaning of the acronym. And the RCP 0.5 is also called the business as usual scenario, which means absence of any politics, mitigation policy, and politics agreed on the reduction of the human emissions. So basically, they assume here that the human emission will increase as they have increased in the recent past. This is considered overly pessimist, overly conservative scenario, because we already started to decrease emissions, and you can see in the graphs in our world in data, for instance, that there is already probably we are close to reaching the plateau, because indeed we have set up several policies, and these policies actually don't really depend on the political oscillation. So, I mean, it is unlikely that in the future the production, the emissions of CO2 will raise again with a great increase. In the future, it is very likely that whatever is the result of the election in the United States, it will continue to be mitigated. Okay, and these scenarios, just to give you an idea, I think I have a graph somewhere. Let me see.
RCP stands for Representative Concentration Factor.
Okay, yeah, okay, representative, yes, thank you. And I think I have a graph. Let me see. This is temperature. So the graph is it's not here. Let me just check. Anyway, I get there are several graphs over the web. Anyway, .5 is business as usual. Usually, people use in the simulation RCP 4.5 is an intermediate scenarios, and which assumes that the emissions will peak around 2040 and then will start to decrease. Now, some recent interpretations argue that probably we already reached the peak. By the way, by 2050, Europe means to become, aims to become carbon neutral. Carbon neutral means that the emissions should be, in a way, eliminated. This is overly optimistic. We will never be carbon neutral by 2050. But I think that indeed the assumption of the peak around 2040 and then a decline, it is reasonable, because, as I said, there are some interpretations that concluded, some studies concluded that we are very close already now to the peak. Because indeed, with the increase of renewable energy, keep in mind that, I mean, energy production is really a huge contribution. I'll show you a graph later on of the contributions to human emissions, but the energy production is indeed very, very important. And there are several emission scenarios which are estimated with a socioeconomic analysis. And these are those that are used currently in making the simulation. As I said, RCP 4.5 is considered to be quite a good indication. Keep in mind that it's a relevant information to be taken into account when we deal with climate predictions. I just wanted to give you an idea, because just to conclude, you know, what is the result of these simulations. And this lecture is quite long. It is very descriptive, and it delivers much more information with respect to what I said so far. I leave it at your disposal if you want to get a larger overview, but I'm not really interested. I don't think you need more than what I already told you. I think it is useful for you to know how models work, but I think this is enough. I just wanted to give you an idea of where we could find an answer to the very simple question, but then how the climate in Italy will look like in 2100. These data are publicly available. So these simulations, which are produced by international research centers, are publicly available. On the other hand, to work with data, with this data, it's extremely an issue because you understand the amount of data that you have. Some of the variables are simulated at daily step over the whole globe from 2020 to 2100. So you get 8 years of data times 365 days times the number of the globe cells. So you understand that it's really tons of data and it's not easy to manage them. So the result is that even if the data are publicly available, to download them and to make even a very simple assessment is not easy. It's not easy, and basically in most of the cases you need some knowledge of coding. By the way, probably you are not a passionate of coding or data analysis. I think that if you made an effort to learn something of coding, it would be an added value to your CV because, you know, okay, a medical doctor, but if you can, if you have this skill of being able to manage some data, to make some statistical analysis, I think it would be interesting. And then at this stage, you may ask me what kind of coding, because coding is something that is not defined. I mean, there are several languages. And my suggestion would be, given that you may need to deal with data, making also some even simple statistical analysis, but you could start with something very simple like Excel. With Excel, you can learn the basis and you can make most of the simple computation that people usually need. So, but Excel, I think, would be really required. But I would go a bit further, and you may think of a software like MATLAB. MATLAB is something, do you know MATLAB? It's a software for making computations and for making graphs. And MATLAB is not free, so this is not a good thing, because today you know that there is a push for open science, open data. I am a fan of it, and so I wouldn't use MATLAB, but I give you a couple of suggestions just to give you an idea. You know how to use Excel or something? Yes. If you have to make a graph in Excel, can you do that? Okay. I would suggest that this is the minimum requirement. If you are a medical doctor, you should gain this knowledge because, you know, it is part of our everyday life. But just speaking on public domain and not difficult to use softwares. Let me open another Google search. There is a software that is called R, and you can find it if you Google for R project. R and dash, can you see on the screen? Okay, R project. And if you Google it, there is this software here, which is quite easy. And I'm not opening it now because it would take like 5 minutes to install it and to use it. So but if you click here, you find this page and download. And then you select a mirror. A mirror means a repository, and it doesn't matter. Choose whatever you want. And then there is a download for Windows, for instance, or Mac or Linux. Windows, and you get the base. You follow these instructions, and then you get an executable file, and you double click on it, and it gets installed. With this software, in a very simple way, you get to a console. A console is a window where you are required to put any input. So these open source softwares usually don't use the mouse to work, and they are not interactive. They wait for a command, but you can perform simple operations like 2 + 2 and produce graphs, and it's not difficult, really. And they have plenty of examples. So I suggest you that because this is becoming really something that it makes a difference in your capability to elaborate data and interact with people. And I want to give you now an example of maps of future climate, because as I said, these data are difficult to get. I can give you an example where you can get data. Copernicus is the European Agency for Environmental Analysis and Modeling. So Copernicus Data Store. Copernicus Data Store, Climate Data Store, Copernicus, you get to this place where you can download a lot of data, but it's not easy to use, okay? But here, you can put indeed Milan and get simulation of temperature, rainfall over Milan, daily time scale up to 2100. It's not simple to use. It's free. You just have to register, but it's free. And in terms of maps, CMCC Maps Climate Italy. These are climate scenarios for Italy. It's the only maps for Italy that I know. And usually when I get asked from people working on irrigation boards or water supply managers, where I can find indication of the climate that we may expect over Italy, I give the suggestion. I say, get the CMCC climate scenarios. CMCC is a research center, is a foundation, so it's a mixed private and public research center, and it means Euro-Mediterranean Center for Climatic Change, and the CMCC stands for Centro Mediterraneo Cambiamenti Climatici, Euro-Mediterraneo, and here they have these maps, which are nice because at least they give you an interpretation over Italy that is ready to use, and provided the network works. Anyway, you get here maps with colors, and they can allow you to understand what kind of changes you may expect over Italy for different, keep in mind, variables, climatic variables. And these climatic variables can become, at the end of the story, health indicators, which we will define later today. So climate scenarios for Italy, and here there is the map. And here now it is in Italian here, but I think there is also the English page. And here you see the maps and indicators. So in this window, you can see a map of Italy with, for instance, temperature, mean daily temperature. And the period is, let me see, you have to select the scenario, RCP 8.5, and the period. So let's get 2021, 2050. So this is the temperature, and you see here 1.5, here the period is 9. 1.5 means 1.5 over the pre-industrial period. Okay, so it means global warming of 1.5. So it starts from 1, because you know that the global warming is about plus 1.5 now. There were articles in the past week saying that we went for the first time at the annual scale above 1.5. Last year it was 1.49. Now it seems that it's 1.52, something like that, but it is provisional. So you don't have to be surprised by the fact that here the prediction is up to 2050 in the green zone. In the green zone up to maybe +2. You see that there are some spots with +2. If we go to 2071, 2100, you see what is the situation. But this is the business as usual. And you know, with these maps, you can get an estimate. If we go to RCP 4.5, you see that there is a huge difference. And therefore, you have to keep into account also the scenario. I hope it's not broken. Okay. Let's move forward now with the next lecture. Just 1 second. I want to make sure that I didn't close. Okay. the registration. Climate change impact on health. First, let me open this link, which is just one slide. And let me start the animation. This is, we are starting now to talk about the impact of climate change on human health, the part that is probably more relevant to you. So, you see that it stops at the end of the story, so don't be concerned by reading everything now. Climate change is in the center, and you see the rotating circle. It's the effect that we believe, the changes in climate that we believe are most effective on the human health. So, rising sea levels, more weather extremes, rising temperatures, and increasing CO2 levels. Actually, increasing CO2 levels, I would say that it's not directly effective on the human health, but we will see more details later. And then in the outer circle, you have the definition of the events that come from rising temperature, etc., but which are more related to the illnesses. And in the outer description, you have the illnesses. So the effects are severe weather, air pollution, changes in vector ecology, vector-borne diseases, and increasing allergens, water quality impacts, water and food supply impacts, environmental degradation, extreme heat. So what are the illnesses, or in any case, the conditions that may have an impact on the illnesses? Forced migration, civil conflict, mental health impacts. The impact on mental health, I was considering it like a side effect, but I realized indeed that there are several people that have this kind of climate panic, climate anxiety, and indeed this is relevant, and especially in the scientific community where there are several researchers concentrating on these issues and probably become more concerned, but there are indeed severe implications. And then there are the
I want to say that I think that's very relevant. That's why during the first lecture, I asked you if we can have more scientific point of view on the question. Because on the social media and in movies and everywhere, it's very spread this way of thinking that I don't know, a very negative way of thinking without looking at the problem. As you said, in a maybe evolutionary way, which is more maybe I don't know, more appropriate to think about the problem. So also I remember when we were in high school, there were all the manifestations for the climate change. So for our generation, I think it's very relevant, and it adds to all the other problems that we have, anxiety and blah blah blah. Also, this negative way of thinking that is due to the at least I can say at least once a day on my feed on Instagram or TikTok, I have one post regarding climate change. Yes. I can say at least one.
Yeah. You know, you're right, first of all, and of course the social media try to amplify the negative feelings. So this is why you get several times these posts, and it is unlikely that they emphasize the positive feelings. It is unlikely that a person goes on the social media and say, today I'm very happy. Usually they go there and say, today I have one more reason to be very depressed. And because typically when people suffer from a concern, they feel like they have to share this. And happiness is a different story. Typically, it's like if you go into a bar and you comment on the national football team. Usually people that go into the bar, and that was in the past an analogy of what is happening in the social media. Typically, they go there to complain or to complain about the government. It's unlikely that a person gets into a bar and says, I'm very happy with this government. Never happened. It never happened. So this is why it becomes so widespread. And, you know, I think it is not a feature of today. I think it has been always like that. There is a trend in the people to emphasize their negative feelings rather than the positive feelings, which I think makes it very important that also we play the role of the positive thinkers when we are instructed, you know, when we are in our field. It's like a medical doctor. I think it is very important that gives a positive feeling to the patient. And I also feel the duty, given that I really look at the numbers, to convey this a positive view on climate change, and positive view, a balanced view, let me say, not overly positive, but a balanced view. So at the beginning, I considered these concerns exaggerated, and then I thought that it was not really a relevant problem, the mental stress. But actually, I perceive that it is very widespread, maybe that there are also other reasons. And then if it is widespread, it must become a concern. And I think that we are talking of a problem that is real, but it doesn't lead to extinction of the human species, you know, and also many climatologists share this opinion. So even if the sea level in the future will rise of 20 meters, and even if the polar caps disappear, the world will be completely changed, but I think it will be still possible for humans to live there. They will have to migrate. They will have to migrate to the north, but it will be still possible, especially because if you look at the progress of our life condition and life expectation, I'm starting the next lecture with this consideration, it is increasing. And every prediction basically predicts that the life expectation will increase. It will reach 90 by 2040, probably. So, I mean, there is no reason to think that with this pace, with this evolution, we will get to extinction soon. Keep in mind that for sure the human species will get extincted in the long future. We know the Earth system is not forever. The Earth system, once that the nucleus of the Earth will become cold, life will disappear. So, I mean, but in the very long term, and I don't think that today the anthropogenic influence will lead to extinction by 2100. Absolutely not. It may lead to problems, but still, I believe that the life expectation will increase. So this is the message that I would like to convey. Like, we are not talking about human extinction. We are talking of a relevant problem. I agree. But I think that we should give our contribution to make clear that it's a relevant problem, but it's a relevant problem like many other problems that we have. I tend to consider the problems that we have in the Middle East now and the war in Ukraine more important than this. This really may lead to the Third World War and to something that is really a disaster in a very reduced time span. So we should be more concerned of this. And climate is, for sure, it is important. Like, it is important water supply, it is important also the medical care. It is extremely important, but it will not lead climate to extinction. But in any case, it is indeed true that many people make of climate an immense problem in terms of mental.
I also think about politicians, and you said life expectancy will increase, but I think il filosofo Galimberti dice che aumenta la vecchiaia e non la vita. Nel senso che like young years are more like if we in young adults have this negative way of thinking, so we are not really enjoying, I don't know, and then we have this other, we will make longer this other part of the life, which is already determined, which is still cool. I don't want to say like being young is cooler than being old, but still, I don't know, we have this. At this point, I cannot say social media. Maybe it's just like politicians that also contribute to this, and then there is like the upper level, and then all the others level are, contributing even more. But still, like it's very relevant. It's very relevant, and I think affect the youngest, because in the past, the youngest people of the past were not affected. They did not have this concern, this way of thinking. We don't have the future. Our kids don't have future, blah blah. And so we have an additional concern, and also we are really, most of us are addicted to social media, so we are exposed multiple times per day to these, and it's very hard if you are exposed for so long time to say no, it's not true. I mean, I know it's.
It's a matter of
it's
philosophy.
Just to say, to say my point of view, but still.
It's a matter of philosophy. I fully agree with you that there is also a political problem, and also in the healthcare system there is a political problem. And the political problem is that I believe we live in a democracy, and the democracy is based on consensus. And, so we have the problem today that the politicians look for consensus rather than looking for the common good, because if you look for the common good, you have to take tough decisions that people don't like increasing taxes is the most, we live in a situation today where the public debt is very high, and it is clear that if you don't increase taxes, how can you improve the healthcare system or climate mitigation, climate change mitigation? You have to increase taxes, but nobody wants to do that. So they react by saying climate change is a global problem. It's a problem for Trump, for Xi Jinping, for Putin. It's not our specific problems, and they resolve the situation by complaining to other people. And this is because they look for consensus. And this is an effect of democracy that we have to expect it. And it's not a result of decay, decadence of our societal system. It's a result of democracy. So the question for the future is indeed, is this political system sustainable? So I'm not sure. I'm not sure that the sovereign countries are sustainable in these terms. They may come to default, like it happened to Greece, it may happen to Italy, it may happen to Europe. And then this may be really a problem. But in terms of, so indeed the attitude of the politician is a problem. But I think overall, and going to the point that you mentioned, I'm not really sure that today the young generation has more concerns that my generation had. If I go back only to my youth, I had your age more or less in the 80s, end of 80s. And I well remember when I was 15, end of 70s, that we had huge concerns because there was the terrorism, there was, our future didn't look bright. There was the nuclear bomb that, and Russia and the United States were continuously fighting, threatening to launch a nuclear bomb over Europe. We were really concerned. We had many protests, and many people were killed in the 70s, both on the right side and left side. And we had several deaths. And it was not really good. So I don't think that now the situation, and now they say people are continuously going into the social. Yes, in my age, people were going to the television and watching the TV all the day. And then the computers came, and there were some nerds working all the day over the computer, even without the internet. So I don't think the situation is really worse than that. And when the philosophers say there is more vecchiaia, more old age, I mean, look at the physical condition of people that are 85 today. And I remember how my grandfather was at the age of 85. I mean, it was a completely different story. And today, if people take care of them, I mean, unless they are very unlucky, we have a very good life expectancy and very good living conditions up to an age that it was unthinkable, I mean, 30 years ago. But if you look at the competition of the master competition, you see people that are 85 running faster than me. I mean, I don't think the situation is so bad. This doesn't mean that we don't have to be concerned. I am concerned by the politics, by the asset of the societal system. I am concerned by climate change. On the other hand, we should not overstate the problems, because otherwise, if you overstate the problems, then you get a societal tension. You know, people get really like panicked, really concerned, and they may react in a way that is you know, unpredictable indeed. And anyway, you have here a first description of the illnesses that may be related to climate change. These are not new illnesses. These are things that probably you know already very well. So there is nothing new, nothing to be particularly concerned. On the other hand, we have to be prepared, because if the dengue is coming in Italy, and you have heard that there were cases already, you have to be prepared for that. Of course. So it is something that is important that we know. So how to study these issues? Okay. Here we have the first list. And then let's go to the next link. Okay. Now, first of all, let's try a classification. I think I have even here a PowerPoint. A classification of the illnesses that may be related to climate change. I anticipate a first very simple classification is traumatic effects and non-traumatic effects. So effects, injuries related to trauma, and okay, let me see. This is the train of thoughts of this lecture. So this is already known, okay? Climate is important, and now medical issues, health issues related to climate. As I said, traumatic consequences and non-traumatic consequences. So traumatic consequences related to the occurrence of disasters like floods, like landslides. So basically conditions that cause a physical trauma, okay? Physical trauma, not just, the trauma can be split again in two categories, the mental trauma and the physical trauma. So of course the mental trauma is something that may be caused also by events that are not really traumatic, like heat waves or event like that. And then we have the non-traumatic conditions. The main component is are two: the cardiovascular respiratory diseases and vector-borne diseases. Here you see that the mental disorder is classified as non-traumatic. Any classification has some gray areas, you know, so just let's keep in mind these categories: trauma, cardiovascular, respiratory, and vector-borne diseases. And let me just go back to here to the web page, because I want to make sure that I'm not forgetting anything. Okay, good. Issues associated with physical trauma and issue associated to non-traumatic conditions. And then non-traumatic conditions, here I adopt this classification: cardiovascular diseases, respiratory diseases, vector-borne, this is extremely important, mental disorder. Now, let me give you an example. One second. Yeah, this one. So this is the annual incidence of the Lyme disease, a vector-borne disease. Do you know Lyme disease? It's brought by the ticks. The ticks are these small parasites that take your blood, and then they basically get on your skin and take your blood. And they may bring a disease which is called the Lyme disease. It's a neurologic disease. And it is not really serious. I mean, it can be treated, and usually it is treated very effectively. On the other hand, it is difficult to recognize it because it may come out after a long period, after you forgot that you had a tick, and the symptoms are something that are not immediately identifiable, are not immediately linked to the Lyme disease. In order to get detected, you have to make several inspections. I had several friends affected because it's quite common, and some of them took really a long time, like a couple of months after fever, weak fever and weakness, and they made several analyses and tests, and finally they remembered that they had a tick on the skin, and they removed it, but they forgot, and then they were treated. In a few cases, it may be serious, because if it's not treated, then it can cause some neurologic long-lasting impacts. And you see the annual incidence of the Lyme disease in the United States, and it's clearly increasing. There is no doubt on that. And it is increasing not only because of climate change, I mean, or not directly because of climate change, because the climate change effect is clear. There is an increase of temperature even during winter, because the ticks during winter, if it gets very cold, they die. But if the weather remains quite warm, then they can survive during the winter. And the increase of temperature increases also the number of hosts. Number of hosts, typically these ticks are, because the ticks are, not all of them may get into humans. For instance, the ticks that the dogs ticks, they don't get over the skin of humans. Typically, the ticks that affect humans are vehiculated by the deers and the other animals of the deer's family, like in Italian capriolo, dino, not only the deers, but also these small, what we call in Italian ungulati. And these are markedly increasing for the fact that they live better in the warm climate, but they are markedly increasing also because of the protection policies. So it's not only climate. So now we protect these species. So they are getting more widespread because they are protected, and they don't have the predators that the humans killed, like the wolves and other predators that we typically kill, because these predators also are predators of the sheep, of the goats, and therefore these are being killed by humans. And in absence of the predator, then the small deers and the deers, they proliferate and they bring the ticks. So this is why we are pushing now for reinstalling the wolves. And then you know the problems. Actually, the wolves are not really a problem. I never heard, I have a lot of wolves in the Apennines close to my home, and I go to the mountains. I never met a wolf, and also I never, we don't have any notice, we didn't get any notice of an attack of a wolf attacking humans. They may eat dogs, for sure, but with the humans, there is no problem. It's a different story with the birds. The birds indeed are dangerous. But this is why we aim also to reintroduce the predators. And this is a clear example, the Lyme disease. It's an anticipation. And we will discuss the Lyme disease and other illnesses next week. And let me just go back to the beginning. So the above these medical issues can be divided into short-term impacts, like the physical trauma may be a short-term one, but they may be long-lasting. For instance, the mental disorder may be long-lasting. And so what are, in particular, the variables we are interested in? Local climate variations and local conditions of the socioeconomic context, like accessibility to healthcare, water security state, agricultural production, local feature of populations, like age, nutrition, health state, and climate change adaptation policies. These are all local things, local details. You see the importance of the local situation. And the health, if we want really to look at the variables, may be affected by these variables. Why I am focusing on the variables, like temperature, extreme rainfall, peak river flow, which means risk of flooding, extreme wind velocity, solar irradiance, which is related to the consequences, impact of heat waves. Why I am interested in these variables? Because we need to quantify in some way what can be the impact on the human health. And therefore, we need to identify some indicators of this impact. These indicators are called health determinants. And I think they are introduced somewhere here. We will discuss them next week. So we have to identify the health determinants, everything is written here, that are related to climate change. So we have to identify, depending on the situation, depending on the climate predictions, on the climate scenarios, we have to identify what is the relevant variable that we can use as an health determinant. And can be a climatic variable, but can be a societal variable, like some indicator of the efficiency of the healthcare system. And then through the quantification of these health determinants, then we come to a quantification of the health impact, and we will see next week how to do that and what are the illnesses. We will discuss with some more details what are the illnesses. We already discussed two illnesses, the Lyme disease very briefly and the schistosomiasis, the first lecture. Do you have any question? You like it? Okay, thank you. I hope that you are frank and sincere in your assessment. Let me just stop the registration somewhere here.